All right, everyone. Today we are going to talk about emissions. This is going to start as somewhat of a broad topic about why we need emissions on vehicles, and then we'll take that, look at just kind of general air pollution impact globally, and then how does that impact us in Illinois, and then down into specific vehicle systems. So our objective is just to kind of understand why we need air emission and vehicle emission systems and what their goal and intention is, and then get into the specifics about what are these systems, what are the components, how should they function, what's the theory, as well as what is the service and what are some of the common failures. Those will be our goals as we go through this. And emissions equipment is going to span at least a couple of weeks, perhaps 2 or 3 weeks of our time together. So with that said, let's get started. And so vehicle emissions exist for many reasons, right? The primary driver is that we've got a global concern for air pollution. And so for us, domestically in our country, the EPA or Environmental Protection Agency are the ones tasked with coming up with the laws, legislation, regulation that exists around this, as well as enforcing it. And so these guidelines constantly change. Manufacturers have to conform to these things. So once they put, say, a mile per gallon or fuel economy target in place, it's usually tiered over a certain number of years, but manufacturers have to hit that in some fashion. There's a lot of nuance and ways that those things get done. There's a reason why General Motors can still sell a Corvette that gets minimal fuel economy, but then they also sell high fuel efficiency cars or even electric cars on the other side of things. There's these credits and things that go on with that. But without a lot of specific on that side, keep it kind of in the service and awareness side. Let's start with this. The idea that here from 09 to 12, millions and millions of cars were sold. And this is just vehicle sales. So if you take this number and really think, how many cars are out there driving right now? It's just an incredible number, right? And so when we think about this and apply this logic, well, I just have one car. Does it matter that I took the cat off? Well, your car by itself, maybe not, right? But we together as a group have this diligence and where we're called to maintain the environment. And so we had to think about the impact that occurs at scale. And so keeping these emission systems going is ultimately going to cost some money to us as vehicle operators, right? And provide some work for us as technicians. And so who's responsible for that? Well, early on in the vehicle's life from point of sale, the first 2 years or 24,000 miles, the manufacturer has to warranty performance items, right? So this is fuel, ignition, other emission systems. Most manufacturers exceed this. Some time ago, Hyundai was one of the early manufacturers to really push a bumper to bumper warranty and really take it, out past 40, 50, 60,000 miles. And so a lot of manufacturers have followed suit from a marketing perspective to put that kind of coverage on things. But one of the other things that happens is that from an emissions equipment standpoint, those components have to be warranted for 8 years or 80,000 miles. So if it's a component that has a major impact on emissions, that's got to be warranted for a pretty long length of time, right? So the CAT is one of those things. Interesting on electric cars, the battery has become one of those things, especially hybrid cars, I should say. And other control equipment falls into that as well. So going back to this idea, why do we need this stuff? Think about exhaust and tailpipe emissions. Think about where they go. We have a pretty good way of monitoring the air quality, right? So this chart's from airnow.org and shows the air quality index for different areas across the country. So on this specific day, whenever I pulled this, you can see these different trends, and they don't necessarily match metro areas, right? So the interesting thing about this chart is that it not only drives at specific pollution elements. It's just a general air quality. And they also express it in a chart form like this. And so if you look at Champaign-Urbana, we're at a 31, pretty low. If you look down there in the chart, the key, it says good 0 to 50. We're in that 0 to 50 range. If you look at Chicago, you look at north and west suburbs of Chicagoland area, they're in the 50s, right? And so some of that's like, yeah, okay, there's a higher concentration of people in that space. We kind of expect those numbers to be higher, right? The other interesting thing is that weather certainly plays a role in this kind of reporting. So if you look at a single day and time, if it was windy, if it had just rained, all of these things are going to impact this number. And so really to understand how this goes, we got to look at a longer period of time. The other interesting thing on this chart is that it talks about the critical pollutant. So you notice most of them are particulates. Well, a particulate can be sulfur or something from a tailpipe emission, like in a diesel vehicle, or it could be just any particulate in the air, right? So if you think about this October kind of late fall time frame, a lot of harvest is getting started soon after that, or around that time. And when you're harvesting in the fields, we see it here locally that just about the whole town is covered in a dust and a film, right, from harvest, right? All the corn stalks and dry material that gets stirred up. So just a good awareness to think about. Think about that 50 air quality number. Take that forward, look at this from the other side of the world. Similar day in Shanghai, the air quality index was almost 5 times worse than it was in Champaign, right? And so is this all vehicle emission? No. It's probably largely manufacturing and industrial output, but it drives the idea that, again, in scale, lots of factories or lots of cars in a condensed space, they have an impact, right? So here's a visual of that impact. The left side is smog from air pollution. The right side is the same picture, it's just been cut after it had rained, right? So when it rains, that is somewhat of a natural filter to pull a lot of things out of the air, and you can really see a dramatic difference, right? It's just devastating how bad that is. At street level, right? Could you imagine? Walk out your door, this is what you're met with. Just terrible, terrible environment to live in. I can only imagine. One more from that area, satellite image of pollution. The left side, you can see there's definitely a weird darkness to those. On the right side, we got nice, fluffy, happy white clouds. So again, just reasons why we need to pay attention. We need to find ways to utilize these systems, keep these systems operating, even as we go through our life as a tech, or if we're a hot rodder race car kind of person. We got to acknowledge that a day will come where we've got to have a race car with a cat. I think that day is it's going to come sooner than we think. So one more picture, and this is a recent one. So talking about just impact of numbers and things that are happening. These two images, BBC had published this. The source is from NASA. This is a measurement of certain nitrogen elements between January and February in China. And so the difference there, China was very much ahead of us with COVID-19 and lockdown. And so the January really represents their normal sort of patterns in industry and commerce for them. And then the right is with them on lockdown, with all these things largely closed. It's just incredible how quick, when you take the sources away, that air quality number and that pollution really diminishes. And maybe you've seen some news articles about this stuff before, about like in Italy and the canals, how clear the water has become, just because the human element of pollution has gone down. So that's obviously on the other side of the world. How does that play out here? We in Illinois, depending on where we're at, do work with air emissions. And we've got organization called the Illinois Air Team. This started in the late 80s. Their kind of jurisdiction and space that they operate in is Chicagoland as well as East St. Louis. And what that means is if you're in either of those spaces, those areas, or your vehicle is registered in those areas, you've got to have emission testing done. And if you go back to the beginning of their origin, that started with idle air quality testing. We'll talk about what that is. They then moved on to this thing called IM 240, right? So we'll talk about that. That didn't stick around for very long. That was a pretty comprehensive test, but also a pretty demanding test on resources. And so today, what they do is all OBD2 monitor based. And so that means anything 96 and older in a lot of cases is exempted, at least as of this 2007 when the document I pulled this information from. All states do things differently. So this again is just Illinois. If you go to other spaces like California, they've got more stringent and more comprehensive kind of regulation around their vehicles. So here in Illinois, we've got things a little bit different, right? But if you fail your emissions test, if you're in either of those areas, it can impede your ability to update your registration, or update your vehicle sticker. And so back in 2012, about 2 million vehicles were tested. About 7% failed the test. So pretty high pass rate. Basically, there's some parameters in order to get your vehicle tested. Check engine light fails you from the get-go. So there's some good that comes out of this, that we're keeping cars maintained. We're thinking about emissions. That's, I think, the top goal. But also you think about from the service end for us, it helps reinforce to certain customers that, hey, you really should take care of the issue that's turning your check engine light on. You should get that fixed. So testing locations, right, again, concentrated in Chicagoland and the East St. Louis area. If we think about globally, or not globally, but nationally, where is this kind of stuff done? It really speaks to all the metro areas. So if you look at the bottom right, different places where things are going to get tested, you see kind of hot spots of Chicago, St. Louis, Atlanta, and kind of all the central part of the country, and then the coast, fairly heavy as well. So some of the other tests over time, I mentioned the idle air quality test that used a thing called a 5-gas analyzer. We'll mention that. But later on, they went to this IM 240 test, and it really was a good comprehensive test. It utilized a dyno, so the car had to be put on these rollers of a dyno and then driven. And so this is a chart of speed versus time. And you're probably thinking, hey, that looks a lot like a drive cycle, because it is, right? So basically, they would put a car through a whole drive cycle while watching what came out of the tailpipe. And so you can imagine this is the most comprehensive way, because this is similar to what a vehicle's calibration or regulation of emission would be for a manufacturer. So a very, very good audit. But every test facility would have to have a dyno. You'd have staff to run this dyno, drive the car, right? Do all this safely. And so a lot of resources would have to go into this. And it's also a longer test in terms of setup and operation. And so that didn't stick around very long for us, where we moved along away from that. So now what we're doing is just looking at, does the car have any codes that are emissions related, and will the monitors complete? And using that information to make determinations. Basically, we think if the EVAP monitor will run and it can do that self-audit, then it must be in good shape. So those are the things that we're employing. But kind of fun, it generates some data. That's a little bit old, but here from back in 2007, what were the most popular codes stored when people came in? And so in this pie form, then I'll switch here to, this is count and everything else, right? So this has got your code on the left, NC versus C, right? So non-continuous versus continuous monitor base, and then how many occurrences, and then the description of the code, right? So number one hitter, catalyst efficiency, below threshold, right? Got the most hits. Not too surprising, right, that somebody might go with an ignition misfire for longer than they should, and they burn out their cat, and now they get a PO 420, right? And then you keep going down this list, and those of you that have been working in a dealership or a shop, if you've been a part of pulling codes, you could probably see that, yeah, those are a lot of the codes that I see, right? That you see cat codes, you see system lean or EGR and EVAP codes, misfire codes. These are all really the prevalent things that we as technicians deal with. And they all relate to emission systems, right? It's a great reinforcement of why we're going over these things. And so if we reflect on why, we're going to think about this, right? So what goes in, what comes out? When we think about combustion, we're looking for air, fuel, and spark. Those are my three things that I want to put in, and I'm looking for combustion and power to come out of it. And so where we're at today is we're focusing on that outcome. What's coming back the other side? In car world, we look at really 5 outputs in total, and we focus on 3 major ones. And so my 3 major ones, first is hydrocarbons. We often express that as HC. So hydrocarbons is just unburned fuel. We know that a combustion engine, internal combustion engine, is not 100% efficient. And so some of the fuel that I put in there is going to come out the other side. Our goal is to minimize it, but that's going to be the case. The next one is carbon monoxide, CO. This is generally a byproduct of incomplete combustion. It is poisonous to us, right? It's an odorless, clear gas, so we're concerned with that. And then the last of the majors is oxides of nitrogen. It's generally referred to as NOx. And this is a gas that gets formed by high combustion temps, and it's one of the biggest contributors to ozone issues and smog. And so it's something that's very much on our radar to deal with and manage. The other 2 that we look at or monitor with tooling, carbon dioxide, CO2, as well as oxygen content. Water we see occur, but we generally aren't measuring that in any kind of quantity, right? So those are some of the outcomes. If we go back and think about what went in, what's in our atmosphere right now, majority of it is nitrogen, right? So almost 80% of it's nitrogen, about 20% is oxygen. We have some argon and some other trace things, but these are the things that we're starting with. And so you think about, well, why did certain things come out? Well, there are, again, inefficiencies of this engine design. One is that quench zones where the spread and expansion occurs will trap unburned fuel, right? So hydrocarbons getting stuck at the edges, around near the rings, all these different places is one of the reasons we have hydrocarbons as an emission. When we hit combustion, we take our hydrocarbon and our oxygen, and through combustion, some of those split apart and create other compounds, right? And so some of the carbon, some of the oxygen, right? You can see where we get some of these byproducts as we go through combustion. When we get additional high temperature, we form other compounds. So one of the things we mentioned, NOx, right? NOx is generally higher whenever combustion temperature is higher. And that's because of the nitrogen and oxygen elements forming together through that process. So how do we look at these things? We've got some specialty equipment. So an exhaust gas analyzer is one of those things. These are often sold in 3-gas and 5-gas analyzer forms. This here is an SPX or OTC tool. We've got one of these in the shop. It's not good when it sits a lot. They've got filters. They have to be calibrated. So you can imagine when a tool like this sits, it often doesn't perform very well. But it has been a commonplace for a lot of shops. And I see a lot of creative ways to use this in other diagnostic work. And so if you see this in the shop, it's worth getting out to see if it works and kind of playing with to understand it. Because being able to measure something like hydrocarbons can be really useful. You think about a head gasket failure. If you can measure hydrocarbons out of the expansion tank or the radiator neck, that's telling you something, right? And so this tool's got some pretty cool use beyond what we're talking about today. So if we take all those outputs and graph and map them across different engine operating conditions, so the bottom scale on this is my air-fuel ratio. Dotted line across the center is my stoichiometric 14.7 number. And you can see how they all interact. As I go really lean, I see my NOx peak out, right? Because a lean burn is much hotter than when it's overly rich. And you see a lot of them dip down at that 14.7 number. And so we're always trying to chase this with calibration and other things. And so there's a trade-off. Certainly there's a compromise. And the systems that we're going to discuss are aiming to help balance that compromise as best we can. We got to remember that how we design our engine calibration is going to have a big impact on this too, right? And so this chart, going back and thinking about my standard O2 sensor and how narrow that window is, that is really the reason why it's almost standard for us to see an air fuel sensor today, is because it's helping us move that mark as we need it to be most efficient, but also to have the least emission output. And so beyond just calibration, we realized some time ago that we needed additional pieces and components to help manage these emissions. And so we have emission control devices. They're things, they're systems, they're components that all work together to try to control the tailpipe emissions, right, exhaust emissions, and also evaporative emissions, right, which is hydrocarbons in our fuel tank, and we're trying to contain them, keep them from going to the atmosphere. And so the earliest system that we can think about and look at is in the 60s, PCV, or positive crankcase ventilation, came about. And so there were a lot of different variations of this system. Lots of different components for all of these systems. One of the things that we're really focused on is that we need to change how the engine operates at times to lower emissions, but also the engine needs to be warmed up as quickly as possible, right? So to be effective with reducing output, we really got to get to operating temperature quickly. And we've got to have the engine running in good shape without misfires as well. And so vehicles that show signs of high emissions need to be looked at for a variety of things, right? If they have high emissions output, it could be fuel trim related, it could be a code, could be all these things. It could be something as simple as temperature, right? Cooling system malfunctions are going to lead to different emissions, because if my temperatures are too low, hydrocarbons and CO emission go up. If my temp becomes too high, it's running hot, right? NOx is going to go up. And so a variety of things that holistically we got to pay attention to. So go back to that kind of first early system, PCV, or positive crankcase ventilation, started in the 60s. It was intended to recycle blow-by gases from the crankcase by putting them back into the intake manifold. We knew early on with engine design that we needed to vent the crankcase in some way, and so early vehicles use this thing called a road draft tube. Kind of interesting thing. We'll look at a picture. Racing applications, we use other methods, right, to clear the crankcase. We use catch cans, things like that. But our goal is to clean the fuel and water moisture out of the engine oil, because it's going to extend the life of the oil and allow that oil to do better work over time. This is that road draft tube idea. Pretty simple setup. We put a breather and a filter, more or less was a filter on one side of a valve cover, put a tube on the other side. That tube would draw down far enough that it would see the low pressure zone underneath the car, and then that was enough to create a draw to pull vapors and things out of the crankcase. So you can imagine that crankcase vapor out spot was just going to atmosphere. It was going onto the road. So not a really great solution from an environmental standpoint. It helped the engine oil, but not a great solution long term, right? It certainly was something that we knew we could be better about. So our modern PCV system has got a handful of things. It's going to operate with a valve so that we can modulate when things occur, right? Different times of engine operation, different engine loads. We're going to use some hoses to route these vapors and things around, connect that valve, and that's going to require that we have access to the engine crankcase in some form, as well as access to the engine manifold vacuum source. And if we put that in as a picture, a diagram, look at my red line coming in. When my engine's in operation, I've got this fresh air that comes through the air cleaner, gets metered in this case. I'm looking at a mass airflow car. Then you see this extra tube that comes off. That extra tube is my fresh air inlet for the crankcase for the PCV system. So the air's been metered. It goes through that. In this case, a V-style engine goes through one valve cover, is able to collect these hydrocarbons, its moisture in the crankcase, goes through the other valve cover where it's met with a PCV valve. That PCV valve helps me with when flow occurs or does not occur, and then those vapors go through the intake manifold into the combustion chamber to be burned. So when all goes well, it does a great job of pulling those things out of the crankcase. You could imagine by looking at this and thinking about metered air and those elements, if I have a breakdown, if I have a leak, it's going to create some problems, right? So on the right side of that, with the PCV valve, this is a cutaway illustration of a valve. I've got two different illustrations to show you, but it shows the three modes of operation with one of these valves. Idle or high vacuum, low vacuum, and if I met with pressure at the other side. So starting with the idling one, with high vacuum situations, we have a low flow. Basically, there's a spring, there are two orifices, and high vacuum will overcome the spring enough to restrict flow at the top orifice and open the bottom orifice. During acceleration or lower vacuum, that spring tension helps keep this in the middle, and then at backfire, the pressure of a backfire or pressure will push it closed, and then there's no flow. This picture does a little bit better job of looking at the two different orifices and how they interact. If you look at the bottom, it's got a taper seat, similar to like a pintle. Same with the top, but it has a much more shallow slope to it so that I see these different elements. So on idle or high vacuum, I'm overcoming the spring, and I'm met with this very metered orifice size at the top of the valve. And so I'm seeing some flow occur, but it is restricted intentionally. If we go to the heavy load situation, manifold vacuum is going to go down, and so this valve and the two orifices, the valve that moves in the center becomes somewhat in the middle, and so now I've got a higher level of flow because my orifice is less restricted at the top, right? And so this is the way that it can dynamically change based on what's happening within the engine. And so if we think back to our days of talking about vacuum and just engine theory, right? What's manifold vacuum created by? The piston going down, right? Drawing down of the piston creates my vacuum within my manifold. It's highest at idle, and it drops during acceleration, right, or high load situations. I also want you to think about what's the source of blow-by gases? Where are those coming from? What is combustion going by that creates a blow-by gas, right? A blow-by gas is combustion that has gone past piston rings and now ended up in the crankcase. And so those become other elements that I've got to manage with this system. And so when the system fails, a whole bunch of different ways, right? But if I have limited vacuum or I have a vacuum leak, that's going to impact the system. If my valve can't work, it's plugged up, it's stuck. If one of my hoses is restricted or a hose has cracked, all those things are going to create issue. Or if I have excessive blow-by because of a mechanical engine fault, I may see that in my PCV system. So another thing that can occur is I can be led to, hey, do I have a PCV valve or system issue that could actually be caused or exacerbated by a mechanical failure, right? So I've got to think about this whole system. How do these things work together so that I can make those calls as I met with them? Another interesting thing is that PCV in a lot of vehicles is monitored as part of OBD2 monitors as a non-continuous. And so they generally use a couple different pieces to try to look at, is the PCV system operating as it should? So here's a takeaway description from all data. You could pause it for a second and read through the whole thing, but it gives you an overview of what the PCV wants to do, right? And then it talks about that on this Ford in particular, is a 2010 Mustang, that they've got heated systems out there as well. And so one of the challenges that we've got with PCV is that oil in these vapors, there's moisture content and there's oil content in these vapors typically. And when those freeze, they can do a lot of damage, right? When water freezes, it expands. And so that can create an issue where we could crack plastic. Another interesting thing that I'll detail on a side video or side presentation is that if it's frozen, it can completely block off your PCV system and then cause the crankcase to go in vacuum. And that can create some really interesting things. General Motors has had some issues with rear main seals and other issues because of that situation in extreme cold temperatures. So Ford wanted to be ahead of that, saw that as an issue on some of these vehicles, and installed electric heaters to help combat that, right? So that's another way for us to try to look after the health of this system over time. The monitor itself, they talk about what kind of code it's going to throw and what it's going to do. It basically looks for changes in manifold vacuum as related to the PCV valve opening and closing in different situations. So with that, we'll move on. That's all I've got for PCV valves. The next part of this, I'll put a lab and a video up for PCV valve inspection. So I made a video with our 2005 Stratus, went through where's the PCV valve, where are all these components, and then also talked about testing. What's the testing that I can do to audit this? So we'll look for that soon. I hope you enjoyed it. Take a look at Cobra, make sure you're up to date. Take care.